pleased to be here and to have the opportunity to present you yet another aspect of this reactor for the third time today. First, it was presented by Simon on a more scientific way. Then I presented a bit more practical way, and now I will go all the way to the practical aspects. As you can see, the title is Risk-Based Analysis of whatever. It is something in the scope of risk-based inspection, risk-based maintenance, risk-based whatever you want. But the point is that we need something to bridge the gap between engineers and management. We need, as engineers, to present to the management in as simple way as possible what is the situation once we find, let's say, a crack or a defect which is not acceptable by standards, and then the question is what to do with it. The question is not as simple as repair it or replace it, because in many cases it's not necessary to do it, and in other cases management would simply take a risk even though it's too big. But if we have something like risk matrix to show them in a simple way which risk they are taking on, at least we are free of any responsibility anymore. So, starting from the very simple definition of a risk being the product of probability and the consequence, we can plot a risk matrix with some green area, with some less green area, maybe yellow, but it doesn't look like yellow, then some red area, and then some very red, and some do not go there area. So this extreme field in risk matrix is about the highest possible consequence and the highest possible probability. Of course, it's very simple, but then again, it's not so straightforward what is the probability and what is the consequence. I will try to now explain a few more details. For example, this approach was studied extensively as the European project, so-called RIMAP, risk something, from 2001 till 2004, and it was introduced to offer European standard for risk-based management, including inspection, maintenance, and control. It was produced specifically for some critical industries, petrochemical, chemical, steel, and power generation, but it's not so much widely applied, and one of the reasons is that it's a bit complicated. So here I will try to simplify it and to make this approach understandable even by the management. And that is a risk matrix in nice colors, like traffic lights: green, yellow, red. Now, some more details. Consequences, you may just say at once, if we consider an airplane, consequence is 5, because people will get killed if it crashes. But other than that, or some other specific situation, we have to deal and to consider health, safety, environment, business, even reputation, as you will see in the following slide. Something like that is written here, and starting from 1, which is the small consequence, up to 5, which is very big one, you can see how we can estimate what the consequence is, just in this descriptive way. So here you can see this traffic light maybe much better than in the first slide. So if management sees something in the green field, it's okay. If they see something in the yellow, they should think about it. If they see something in the red, they should do something about it. Now, how do we deal with the probability? That's very interesting question. I see at least one mathematician here who will criticize me later on because probability here will be quite arbitrary term. Because with pressure vessels, probability, if we consider it as a number of unfavorable events with a number of operation hours or so, we will always get 10 to minus 6 or something. So that's not the way we are dealing with it. I'll come back to this just for a moment. There are some other ways to deal with the probability, and in the scope of that also to take it as just arbitrary term, not really probability. So, to be more concrete, there is a standard API 510. There is a procedure API 581. And that procedure, as well as remap, is very complicated. This is such a thick handbook. To make any estimation or probability according to these procedures, one needs at least, I think, 7 days or something like that. In a situation when we find the defect during, let's say, regular inspection, we typically do not have 7 days to make an estimation about the probability or about the structural integrity or whatever that we present to the management. So once we find a defect, management would ask us what to do, and they expect answer now or an hour before or something like that. So what we really want to do is to use something simple, some engineering tool which is reliable, which is conservative. And for static loading, for pressure vessels, which are typically statically loaded, there is a failure assessment diagram. Very nice engineering tool which enable conservative and reliable estimation. I will show later on how. And also, if we deal with fatigue, there is yet another kind of a diagram, something like crack length versus number of cycles, which enables about the same. So, in this case study, which is static case, you know already about this reactor. There is basic data here, including welding. What I just introduced, I will now explain a bit more. I lost my pointer for some mysterious reason. Oh, here it is, somewhere. So, this is failure assessment diagram. This is the limit curve. If we calculate a point using x coordinate based on net stress divided by critical stress, and our y coordinate based on k factor divided by k1c, which is relatively simple, especially for simple geometries, and pressure vessels are typically simple in geometry, then we can get the point somewhere on this plot, hopefully inside the safe region, or maybe outside of it. Now, if we are inside, there is a very simple reasoning that having a point, let's say, somewhere here close to the limit line is completely different situation than having the point somewhere here close to the 0 point. In other words, if the point is here, probability of failure is very low. If the point is here, close to the limit line, probability is very high. And by saying that in descriptive way, let us also assume that there is a proportion, simple proportion. If the point is here, it is, let's say, about 5% to the limit load, so the probability is 0.95. If it is just here, maybe it is 0.05. I do admit it is arbitrary, but trust me, it works. So we use it and we don't much excuse it. And of course, by doing so, we always do it in the conservative way. So, more concrete, in this case, as already explained, there is a set of values for K1C, for new parent metal, exploited parent metal, heat affected zone, also new and exploited, and well metal, just new one, since it was the best one actually. Critical, you can see at once, would be this at the 540. So if we keep in mind that K is something that we calculate and then we divide it by appropriate K1C, we get a set of Y coordinates, whereas the X coordinate is fixed, it is just net stress. For the assumed crack, which is about 40% of the cross section, net stress is 0.36 once divided by the yield strength at the elevated temperature. So our points are somewhere along this vertical line, and sorry that they are not marked. I tried to do it, but I failed. So I have to just show them. They are in between 0.85, which is here, down to 0.56, which is somewhere just where the safe is written. But it's not scientific point of view that I want to emphasize. I would rather like to emphasize this. Having these coordinates, these points that you actually couldn't see except that I show them, we can present our case to the management like points which indicate space metal and weld metal as new material. They would be in the green field here. By the way, consequence category was estimated as 3. This reactor would not make big fuss if it even explodes, because it is inside some plant, old plant, not very expensive plant, nothing spectacular, but then again, it's not that naive as well. So consequence category was estimated as 3. And then these 2 points in green field, once again I lost this point. Okay, I'm probably shielding it with my finger. So hopefully now it is okay. Somewhere here we have quite safe situation, but then again, once we go to the exploited old material, we increase the risk to the red and to the to the yellow and then to the red region. So if we have to decide together with the management, or at least to present them the case, we would say that this plant should not be used anymore with old base and heat affected zone material, because that would increase the risk from the safe green area to the alarming red area. And then again, it's up to them to decide. Just to note that we engineers, of course, know how material heterogeneity affects risk, but managers do not. So you tell them, to the manager, that heat affected zone has low fracture toughness because of a long exploitation period, they would just look pale at you and what are you talking about? So this is the way to bridge this gap. And that is about also the conclusions. Just to notice that we have now active new technical committee 12, which is about risk-based analysis and especially focused on large structures. Thank you.
Thank you very much.